everyone, thanks for joining me today. We're here to talk about volume. Now remember what volume is. Volume is a numerical measurement of how much stuff you can fit inside of something. So what you should have done prior to joining me today is each of you should have made a box. Everyone would have started with a piece of paper 8.5 by 11 inches big, sort of like this one. And from that piece of paper you were told to cut out squares from the corners of different sizes. Some of you did squares that were really teeny tiny and only 1/2 inch on a side. Others did ones that the square was 1 inch on the side, all the way up to 4 inches. So I made some boxes of my own. I made the first one by cutting out from each of the corners a square that was 1.5 inches on a side. And when you fold up the side, you can see the box isn't too deep. And so those of you who made a box, kind of like this one, where the squares were 1.5 inches on a side, yours should look like mine. I made another box by cutting out squares that were 3.5 inches on a side. So this is what it looked like after I cut out my corners. And when you fold it up, you can see it's much taller than the other box. The base is smaller though. All right, and if you compare these two or look around the room at your classmates, you'll see that even though you started out with a piece of paper the same size, your boxes look really different from each other. So I have a computer animation that will show you some different ones side by side compared to each other. All right, so this is the first one. This sort of looks like maybe it was a box that was created by cutting out one of those teeny tiny squares from the corner. So you can see that's really not too deep at all. This green one, maybe that's the square that's like maybe the one I did. And this last one, maybe a square that's maybe 3 inches or so. But you can see how different they look, even though they all started out with the same size piece of paper. So what we're going to do now is you should all have a handout, and we're going to work our way through that handout. And the first thing we're going to do is make sure we have all the dimensions of the boxes depending upon the size of the square that you cut out. All right, so let me make sure all of you have the same handout. I have it here on my computer to bring up. All right, and it's 2 pages, and on the second page is a graph that we'll be getting to in a minute. Okay? So in the middle you'll see a table, and we're going to be filling that out in just a minute. But the first thing we need to do, remember how you get volume. You get volume by doing length times width times height. So we need to figure out for all these different size squares that we would have cut out, what the length, width, and height of each box would be. Now if you take a look at your boxes though, I bet you can figure out what the height should be. The height is always going to be the size of the square that you cut out. So for all of our heights, we can easily fill those out really quickly. The trick is going to be the length and the width. All right, so let's get started. So for a square that was 1/2 inch on the side, the height of the box is going to be 1/2 inch. The length is going to be 10, which if you think about it, hopefully that makes sense, because the paper was 11 inches long. So if you cut out a 1/2 inch on either end of the paper, what you have left in the middle is 10 inches long. And a similar thing on the width. So if you cut out a 1/2 inch square on either end, you have 7.5 inches remaining. All right, so that's what we're going to fill out for all of these different size squares. So the next square was 1 inch on a side. That makes the length 9 and the width 6.5. And I'm just using decimals because it might be easier for our calculations later on. The next box would be 1.5 inches high. That makes the length 8 and the width 5.5. A 2-inch square, that's going to give us a box that's 7 inches long and 4.5 inches wide. 2.5, that will give us a box that is 6 inches long and 3.5 inches wide. And you can see there's even definitely a pattern to these numbers. I'm sure you've already thought of that. A 3-inch square is going to give us a box that's now 5 inches long and 2.5 inches wide. 3.5 high. That's going to give us a box that's 4 inches long and 1.5 inches high. And then finally 4 inches, that's the biggest ones any of you would have cut out. The length is going to be 3 and the width is going to be just a half. That's the boxes that's going to be the shortest. Or the tallest, but the smallest base. Okay, so from this, we're going to calculate the volume. So remember how you get volume, length times width times height. So I'll give you a few minutes on your table on your handout. You can fill out the volume, calculate it on your own, and complete the volumes, and then you can come back and we'll make sure everybody did their calculations correct. All right, so let's see what you got for your answers. So a volume of the first one, when the square you cut out was only 1/2 inch high, would be 37.5. Hopefully that's what everybody got for the first one. Next one would have been 58.5, followed by 66, then 63, then 52.5, then 37.5, 21, and then 6. So even just looking at the numbers, you can notice some interesting patterns. So what we're going to do from this point, on your handout, you'll notice that on the second page, you have a graph. So what we're going to do is take all these values and we're going to create ordered pairs. We're going to create ordered pairs, and the points are going to have an x-coordinate of the height of the box, which was the same as the size of the square that you cut out, and the y-coordinate is going to be the volume. All right, so we're going to take a few minutes to set up our graph with the axes labeled and everything, and then we're going to take a few minutes to plot our points. All right, so I do have a graph here that we can use. And what I maybe would suggest doing is go every other block would be 1 unit. So the x-axis, we're going to have that be the height of your box, which again is equivalent to the size of the square that you cut out. So you can think of it either way, either as the height of the box or the size of the square, either one. And just to make a really nice graph, maybe we'll go every hash mark is a 1/2 inch. So we'll make this first one the 0.5 square we would have cut out. And then 1, 1.5, so on and so forth. So the y-axis is going to be the volume. And remember, the volume is measured in cubic inches. It's always cubic dimensions for volume. And it might be easiest if you take a look at the values we got for the volume. Maybe we'll go up in tens. So this would be 10, 20, 30, up to 70, I think, should be big enough. If you take a look at the values that we got, I think 70 should be big enough. So let's start plotting the points. So the first one was 0.5, 37.5. So you can just estimate the y-coordinate. Obviously it's going to be a little bit past 35, so maybe right around there. The next one is 1, 58.5. Followed by 1.5, 66. The next one is 2, 63. Then 2.5, 52.5. Then 3, 37.5. 3.5, 21. And the last one, remember, was 4, 6. So your points should look like this. So we could connect the points if we wanted to. And one thing that you'll learn later on in algebra is that when we connect these points, they do form a special type of shape. So they're not going to be straight line segments that connect all these points. It is going to be a little bit curved, kind of like this. And if you take a look at it, the interesting thing is a lot of people, when they start a project like this, they just think the volume's going to get bigger and bigger and bigger, when actually, take a look at what happens. There's actually a maximum volume that you can have when you start out with a piece of paper this size and we cut out squares from the corners of the sizes that we did. If you take a look at this, it looks like the maximum volume we get is up around when that size of the square was 1.5 inches, and the volume ends up being 66 cubic inches. And notice how all the other volumes from all the other different size squares that we cut out, they are all less than that. So you really do get a maximum volume that you won't get anything bigger than that. And that's one of the really interesting things about this. Another thing you can do and talk about is, well, what if we wanted a box of a certain size, a certain volume? Well, we can even figure that out, how large the square should be based upon our graph. Suppose we want a volume that would be 40 cubic inches. All right, well, here's 40, all right, because remember, the y-coordinate is the volume, so we specifically want a volume of 40. So if we were to just trace this over, notice how there's two places where that volume of 40 intersects the graph. It intersects right here, sort of looks a little bit past ½ inch, and then up here, maybe just shy of 3 inches. So what that tells us is if we wanted to create a box that was 40 cubic inches big, we would need to cut out two different types of squares, and either one would give us a volume of 40 cubic inches. We could either do a square that was just a little bit bigger than ½ inch on a side, or we could do one that was just a little bit smaller than 3 inches on a side. So this is some of the things that you get into as you get older and you learn other types of math, starting with algebra. That's when you can get into equations that model these things, and you can even then use the equations to determine what is that maximum volume. What if we did want to have a volume of 40 or even 30 or 25? How big would the square have to be that we would need to cut out? So when you get there, hopefully I'll see you again. But in the meantime, thanks so much for joining us today.